Picture a photo of a cat sitting in the top left corner of the frame. Now picture that exact same cat, same photo, just moved down to the bottom right corner instead. You know instantly, it's still the same cat. Nothing about that took any real effort. But to a computer looking at raw pixels, those two images aren't obviously related at all. They're just two different grids of numbers, with all the interesting values sitting in a completely different place. So how do you teach a machine to recognize the same thing, no matter where it happens to be sitting in the picture? The answer is an idea almost as simple as looking through a small window and sliding it across the page. Welcome to the Artificial Intelligence Institute, AYA, Ubuntu Guild's videos on AI. My name is Dr. Dennis Magaya, Chairman, Artificial Intelligence Institute, AYA. Today we're opening up a different kind of architecture, the Convolutional Neural Network, or CNN. This is part 1 of our CNN series. Here, we'll build a clear understanding of how it works and the core mathematics. In part 2, we'll go further into how these networks are trained and used in practice. Recall from our earlier video, a standard feed-forward network takes a fixed size input and connects every single value in it to every neuron in the next layer. For a small handful of numbers, that's fine, but a photo isn't a small handful of numbers. Even a modest image is tens of thousands of pixels. Wire every one of those pixels directly to even a modest number of neurons, and the number of weights explodes into the millions before the network has learned anything at all. Worse, that fully connected approach treats every pixel as unrelated to its neighbors, throwing away the one thing that makes an image, that nearby pixels belong together and form edges, textures, and shapes. CNNs solve both problems with one idea. Instead of connecting to the whole image at once, look at a small patch of it at a time and move that same small look across the entire image. That's the entire innovation in one sentence. Said even more simply, instead of one giant network trying to look at the whole picture all at once, a CNN builds one small pattern spotter and just moves it around the image, checking every little section the same way. Think of a stencil, the kind you'd use to spray paint the same little star shape over and over across a large piece of card. You don't need a separate stencil for every square inch of the card. You cut one stencil and you move it around, stamping the same shape wherever you place it. A CNN works exactly like that. It learns one small stencil, a tiny grid of numbers called a filter, and slides it across every position in the image, checking, does this patch of the photo look like what I'm searching for at every single spot? One stencil reused everywhere is far cheaper than wiring up the whole image at once. And because the same stencil is used everywhere, a cat detected in the top left corner is recognized by the exact same mechanism as a cat in the bottom right. Say you want to detect a vertical edge, a place in the image where dark pixels sit right next to light pixels in a vertical line. You could build a tiny 3x3 filter that reacts strongly to exactly that pattern. Negative numbers on the left, positive numbers on the right. Slide that filter across the image, one position at a time. Wherever it passes over a vertical edge, it lights up. Wherever it passes over a flat, uniform patch, it stays quiet. That's it. That's a filter finding one specific kind of pattern wherever it appears in the image, using the same small set of numbers every time. And here's the part that matters. The network doesn't need to be told what a vertical edge is. During training, it learns which numbers to put in that stencil. Once training is done, the filter is frozen. Inference, actually using the network on a new photo it's never seen, just slides that same unchanging filter across the new image and computes match scores with it. No further learning happens at that point. So, one more time in one sentence, a CNN slides one small learned stencil across every position in an image, checking for the same pattern everywhere. That's the whole idea. Now let's see it in math. Let's understand the maths under the hood. Before we get to the equation, here's what's actually happening. At every position the filter visits, it lines up its small grid of numbers on top of the patch of the image directly underneath it. Because this is the core of everything, let's say it once more. At every position, multiply the filter against the patch underneath it, add up the results into one number, and that number tells you how well this patch matches the pattern. Now here's that same idea in math. For one single position of the filter, match score equals add up filter value times pixel value underneath it for every cell. Slide the filter one step over, repeat, and you build up a whole new grid of these match scores, one for every position the filter visited. The detail that makes this powerful: it's the same filter, the same small set of weights, reused at every single position in the image. The network doesn't need a separate set of weights for the top left corner versus the bottom right corner. It learns one small pattern detector and applies it everywhere. This is called parameter sharing, and it's the direct CNN equivalent of the weight sharing across time steps we saw in the RNN. But an image has far more going on than just vertical edges. Horizontal edges, diagonal edges, particular colors, curves, corners. One small stencil can't catch all of that. The same way one star-shaped stencil can't also stamp a circle. So a real CNN layer doesn't learn just one filter. It learns many filters at once, all sliding across the same image independently, each one trained to respond to something different. Each filter produces its own separate feature map, so the output of one layer isn't a single grid. It's a whole stack of feature maps, one per filter sitting on top of each other. Each filter produces its own separate feature map, which is exactly how the network moves from detecting simple edges in the first layer to detecting combinations of edges that form textures and shapes in the next, to whole object parts several layers deeper. Let's plug in tiny toy numbers and watch one position happen. Say our filter is a simple 2x2 grid. 1, -1 on the top row, 1, -1 on the bottom row. And say the patch of the image directly underneath it at this position is 5, 2 on the top row, 6, 1 on the bottom row. Multiply each pair in place. 1 times 5 is 5, minus 1 times 2 is -2. 1 times 6 is 6, minus 1 times 1 is -1. Add those four numbers together. 5 minus 2 plus 6 minus 1 is 8. That single number, 8, becomes one cell in the feature map. A relatively strong response, because the left side of this patch is noticeably brighter than the right side. And that's exactly the left bright, right dark pattern this particular filter is tuned to detect. Slide the filter 1 pixel to the right, repeat the same calculation with the new patch of pixels underneath it, and you get the next cell in the feature map. That's every position across the whole image. After building a feature map, CNNs typically shrink it down before passing it to the next layer, using an operation called pooling. The most common version, max pooling, looks at small blocks of the feature map, say every 2x2 block, and keeps only the single largest value in each block, discarding the rest. This does two useful things at once. It reduces the amount of computation needed in every later layer, and it makes the network slightly more tolerant of small shifts. If the strongest edge response moves by 1 pixel, the max pooled value often stays exactly the same because the same largest number is still somewhere inside that block. Here's the part that ties it all together. After the last round of convolution and pooling, you're left with a stack of small feature maps, each one a grid of "how strongly did I find my pattern here" scores. Those maps are flattened out into one long list of numbers, and that list is fed into an ordinary, fully connected layer. The convolution layers find the patterns. The layer at the end decides what those patterns together actually mean. This isn't theoretical. Every time your phone unlocks by recognizing your face, a medical scanner flags a suspicious region on an X-ray, or a self-driving car's camera picks out a pedestrian crossing the road. That's a CNN doing exactly what we just described, sliding learned filters across an image, layer after layer, building from edges to shapes to whole objects. Back to the question we opened with: how do you recognize a cat no matter where it sits in the frame? you slide one small learned stencil across every position in the image, checking for the same pattern everywhere. That's the filter, and reusing it everywhere is what we mean when we say the network learns one pattern detector and applies it across the whole picture. Stack several of these filters and shrink the results with pooling layer after layer, and the network builds up from simple edges to complex objects, all without ever needing a separate set of weights for every possible position a shape might appear in. At the end, those detected patterns get flattened into a list and handed to a fully connected layer, which weighs them against each other to make the final call. Cat or not a cat? That covers the intuition and the mathematics, part 1 of this series. Part 2 picks up right where we left off, how CNNs are actually trained, the tricks that make them work at scale, and a real system built on exactly these ideas. If this made sense to you, part 2 will click even faster. Go watch it next. Thank you for watching this Artificial Intelligence Institute, AYA video, brought to you by Ubuntu Guild.